Hello dear students, I am Syed Ilyas, your physics tutor, and today we'll be discussing the topic work, energy and power. Okay, so to begin with, I would like to comment on this thing, work, energy and power, the title topic. So, see, the first thing I would like to tell you is that this work and energy actually are the two sides of the same coin. Okay, so we'll start with the definition of work and then we'll just move on to energy. Okay, and it will be a very easy transit from work to energy. Now, the first thing I would like to tell you is that we'll start with the very simple cases and then we'll make the advancements gradually. The first thing I would like to tell you is that suppose there is some mass m. Suppose there is some mass m, and what can be the simplest case? What I'll do is that I apply a constant force F on this mass m. I apply a constant force F on this mass m, and let's, for the case of simplicity, assume that there is no friction here. Okay. Now, the simplest case is that the force is constant and it is in the same direction as that of the displacement, because you can clearly see that this force will produce the acceleration in this mass and this mass will get displaced. Okay, so suppose this mass gets displaced in the forward direction and reaches here after some time, and let's suppose this displacement is S. This displacement is S. Okay, and it's directed obviously from initial position to final position. Now, when I do this thing, I apply a force and under the influence of that force, I make a body move. I make a body move. I make a body accelerate. Then I will say that the work has been done. The work has been done. And what is the value of the work done? That is simply work is equal to force into displacement. Work is equal to force into displacement. Now, this is the simplest thing I can tell you, that the force is constant and displacement is exactly in the same direction as that of the force. Now, so to begin with, this is the simplest case. Now, I will just make an advancement to this situation. What is that advancement? What I'll do is that again, I'll take the mass m, and again, I will apply a force F on it. I'll apply a force F on it. Okay. And since this force F has two components, one like this and one like this. And for now, we'll be considering the horizontal motion. So suppose the mass gets displaced like this in the forward direction, and this displacement is S. This displacement is S. Now, what will be the force now? What will be the force? Now, this is the force, and what will be the displacement now? This is the displacement, and we can clearly see that now the angle between force and displacement is not zero. That means they are not parallel, they are not in the same direction. So let's call this angle theta. Let's call this angle theta. Now, what will happen if I want to see what will be the work done here? Now, this force has two components, one component like this and one component like this. This component I will call as F cos theta, and this component I'll call as F sine theta. Now, see, here you have to be very cautious. This F sine theta component is perpendicular to displacement, and you know that the two perpendicular vectors have no projection on each other. So that means this displacement could not be under the influence of F sine theta. So F sine theta component is not performing any work. So that's why, if you pay attention, in the beginning I told you that the work is done when the displacement is caused, or when the acceleration in this mass was caused, and the cause should be the force. The cause should be the force. This displacement cannot be due to this F sine theta, because when the two vectors become perpendicular, they become independent. Okay, for example, if I call this I cap, I call this j cap, then you know that I cap dot j cap is equal to 0. Why I am taking the dot product? Because you know that dot product gives the projection of one vector on the another vector, okay, or it's related to the projection of one vector on the another vector, not exactly the projection, but it's related to projection of one vector on the another vector. So I cap dot j cap is equal to 0 implies that there is no influence of the force that is in j direction on the displacement that is in I direction. Okay, so what will be the work done here? So F has two components, F sine theta, F cos theta, and F sine theta is not doing any work. So which is doing work? F cos theta. So I'll say that F cos theta, and then there is displacement x. Now I would like to go back to this. See, here you can clearly see that work, force, displacement. Three terms are there, three parameters are there, but you know that clearly that force is a vector quantity. Displacement is a vector quantity. Force is a vector quantity and displacement is a vector quantity. And there cannot be ordinary multiplication between two vectors. So either it's a dot product or it's a cross product. Now, what I will say is that here, what should it be? It should be a dot product. Why? Because I know work is a scalar quantity. Work is a scalar quantity. Force is a vector and displacement is also vector. So the dot product between two vectors gives the scalar. If it was a cross product here, then we would have got vector here. Okay. So since work is scalar quantity, therefore there should be dot product here. And this dot product, if you see, this dot product can be written as mod F mod S cos of theta. Cos of theta. And here, why we did not have this cos theta term? Because here theta was equal to 0 degree, and you know that cos 0 is equal to 1. That's why we simply got F and S, F into S. That is the first thing that I had before putting the arrows on over here. Okay, and here it's clear that we have F S cos theta. So what is work? Mod F mod S cos of theta. And clearly you know that in the vector form this can be written as work is equal to force dot displacement. Okay, so in the both cases, this is the more generalized case, and this is the special case of this generalized case when theta is 0. Okay, so in both cases you can clearly see that the work is done when the displacement is caused under the influence of the force. And you can clearly see from this thing that the work done can be positive or negative. Why? Can force or displacement be the cause or the attribute to the sign? No. Which term will attribute to the sign? That will be cos theta. Because when I take force can be negative, but when I take the magnitude of force, it will be positive. When I take displacement, it can be positive or negative because it's a vector quantity. But when I take the magnitude, then again it will become positive. So these two quantities are positive. So this is the only term which decides the sign of the work done. This will decide the sign of the work done. We'll discuss about it a bit later. Firstly, let me just give you some very basic things that you need to understand here. So let's talk about the SI unit of the force. What will be the SI unit of the work done? Okay, SI unit of work. So clearly it is Newton, then displaced as meter, Newton meter, because cos theta is dimensionless because it's the ratio of two sides of the right angled triangle. So Newton meter, and this thing, and Newton you can write as kg meter per second square, and then meter again, so it is kg meter square per second square, and this has been given a special name, that is joule. And you already know that the SI unit for energy is also joule. That's why in the beginning I told you that work and energy are actually the two sides of the same coin. Okay, so this is the SI unit, that is joule. Now let's talk about what will be the dimensional formula for work done. So dimensional formula, you can clearly see that it is kg, so it will be m1. Then meter square, so it should be L2, and divided by second square, so it should be T minus 2. And exactly this will be the dimensional formula for energy also. So this is just the basics. Now let's talk about what can we say about this thing, like what would be the sign of the work done, or in which cases work done could be 0. So first let's discuss how we can get work done to be 0. So work done is equal to mod F mod S cos of theta. So here you can clearly see that if work done is 0, then either of the three should be 0. Okay, either of the three should be 0, or any combo. Okay, like it can be force is 0, these two are non-zero. This is 0 and these two are non-zero. This is 0 and these two are non-zero. Or any combination, force and displacement 0. Okay, then if force and displacement are 0, then the theta makes no sense. Okay, because for the 0 vectors, the direction is undefined. Now let's first talk about cases for work to be 0. For W is equal to 0, work done to be 0. Why I am discussing this separately? Because when work done becomes 0, it helps in solving many types of numerical problems that we'll be seeing in the further classes. Okay, so cases for work done to be 0. Case 1. What is the case 1? The case 1 could be that if force is equal to 0, force is equal to 0 and displacement is not equal to 0. Force is 0 but displacement is not 0. Is this possible? Yes, obviously this is possible. How? Because force is not required for displacement. Force is required for acceleration. So there could be a body which could be moving with the constant velocity. So when it's moving with constant velocity, so obviously you know that it is traversing some distance, it's traversing some displacement, okay? So it is displacing from its position. So when there is force is 0, that means acceleration is 0. Acceleration is equal to 0. That means velocity is constant. So that means when a body is moving with constant velocity, although it is covering some displacement, the work done will be 0. The work done will be 0. Okay, so this can be the first case when force is 0 but displacement is not 0. Okay, what can be case 2? Case 2 can be force not equal to 0 but displacement equal to 0. Yes, so this can be the case. So when we are applying force, so there could be some counter forces. There could be some counter forces which could cancel that force, and due to that thing, that particular force could not be producing the acceleration. Okay, that particular force could not make the body go through the process of change in velocity. So in that case, work done will again be 0, because in this product, anything becomes 0, the work done is 0. And what can be the case 3? The case 3 is interesting. The case 3 is that neither force is 0 nor displacement is 0. Then the third factor comes in, that cos theta becomes 0, and that you know cos theta is equal to 0 when theta is equal to 90 degrees. What does that mean? That means if the angle between force and displacement becomes 90 degree, then the force could not do any work. Why? Because I already told you, when the two vectors become perpendicular to each other, they become independent. So now that displacement could not be due to that force, and work is done only when the displacement is due to that force. Okay, so this is the third case. So cos theta is equal to 0, that means theta is equal to 90 degree. That's why when we had this case, that force was like this, and then we had two components of the force. This component was not doing work done in displacing the body like this. Okay, why? Because this component was perpendicular to this. Okay, so this is the cases for work done to be 0. Now let's talk about the sign of work done. Okay, so when we have to take work done to be positive, and when we have to take work done to be negative. So sign of W. So sign of W. Now let's see one thing. Work done is mod F mod S cos of theta. And I already told you that this force and displacement, these are in magnitude, so they will never be negative. So this thing will determine this, the sign of cos theta. Sign of cos theta determines sign of W. So sign of W will be determined by sign of cos theta. Now, if you have seen the graph of the cos theta function, so see why I am taking the angles only from 0 to pi. Why I am taking angles only from 0 to pi? Because the angle between two vectors ranges only from 0 to pi. Okay, because see, if the angle becomes more than pi, then you have to take the smaller angle, and again that is in the range of 0 to pi. So you know that from 0 to pi by 2 it is positive, and from pi by 2 to pi it is negative. So that means if the angle between force and displacement is acute, you get work to be positive, and if the angle between force and displacement is obtuse, you get work done to be negative. So let me see the two cases. See, this is force. Let's suppose this is force and this is displacement. The angle is acute. If force is like this, displacement is like this, then, or wait, let me make it a simpler thing. So let me say that let's suppose there is a mass m and there is a force F on it like this. And this F makes this mass displace like this. Now you can clearly see that this force and displacement are making an acute angle. So cos theta will be positive, so work done in this case will be positive. But if it's like this mass m and the force was like this, the force was like this, the body was displacing like this, force was like this, the body was displacing like this, then the angle is obtuse. But see, this case seems to be counterintuitive, but it's not actually. Why? Because see, I will be considering the work done by this force. Now you will say that if the force is like this, how can body move like this? If the force is like this, how can body move like this? There could be some another force that will be making the body move like this, that will be dominant over this force. Okay, that will be dominant over this force. So that way, that force which is trying to move the body like this will be having the positive work done, but this force will have the negative work done. Okay, for example, let me give you an example. For example, there is a spring that's attached to a wall, and there is a person who is pulling this. There is a person who is pulling this. The person who is pulling this is applying force like this, and the spring is getting displaced like this. So work done is positive. But what is the spring force? Spring force is opposing that. When it is being extended, the spring force is like this and the displacement is like this. So spring will be doing the negative work, but that external agent will be doing the positive work. Okay, so the thing is that what I want to say is that if the angle between work done, if the angle is more than 90 degrees, that it's obtuse angle, then work done will be negative. So here W is positive in this case, and here work done is negative in this case. Now try to understand one important thing that will make you that will help you decide work done is either work done positive or negative very easily. See, I will tell you one trick. See, force is like this. So force has two components, one component like this, one component like this. This component will be doing no work, but this component will be doing work, and you can see that the displacement is according to the will of the force. The force wants the body to move like that, and the body moves like that. If that is the case, the displacement is in the same direction as that of force. That means wherever the force wants the body to move, the body moves like that, then work done is positive. And here you can see this force has two components, one like this, one like this. This component will do no work, but this component wants the body to move like that, but the body moves like that. So when the body moves opposite to the force, then the work done is negative. And then you have this special case when this thing happens. When force is like this, displacement is like this, then if theta is 90, then work done will be 0. Why? Because at 90 degree, at pi by 2, cos theta has 0 value. Okay. So to summarize this, what I can say is that work done is equal to, so work done is positive. Work done could be negative. Or let me first write work done is positive, then 0, and then negative. When it is positive, if theta belongs from 0 to 90 degree, but not 90 degree. So theta is greater than or equal to 0, but less than 90 degree. Okay. So what I am doing, I am putting the equality sign here, but not the equality sign here. Okay. And when it will be 0, when theta is equal to 90 degree. And when it will be negative, when theta is greater than 90, not equal to 90, because equal to 90 it will be 0. When theta is greater than 90, but less than or equal to 180 degree. So that means if theta ranges from 0 to 90, work done is positive. If theta is 90, work done is 0. If theta is from 90 to 180, including 180, and here including 0, then we have these three cases. Okay. So this is what we need to see. Okay, now let's come to the numerical problem solving part of this. Okay, so I'll be just starting with simpler numericals, and then we'll go on to make things interesting. Okay, now the first thing. See, first let me tell you, you know that there are two formulas. One you can write in vector form, f dot s. Okay, f dot s. So this f and S. Since these are vectors, and vectors could be generally three-dimensional, so I can separately write F vector to be Fxi cap plus Fy j cap plus Fz k cap. So what does that mean? That means this force has Fx component in I direction, Fy component in j direction, Fz component in k direction. Similarly, this displacement S could be written as, you know that what is displacement? Displacement is final position minus initial position. So what I can say is that this displacement could be written as x final minus x initial I cap plus y final minus y initial j cap plus z final minus z initial k cap. So this is displacement in x direction, displacement in y direction, and displacement in z direction. You can simply say that it's actually S is equal to Sx I cap plus Sy j cap plus Sz k cap. Then I'm elaborating, I'm expanding this Sx as x final minus x initial, Sy as y final minus y initial, because displacement in x is final position in x minus initial position in x. Displacement in y is final position in y minus initial position in y, and similarly displacement in z is like that. Okay, so if you see these two things, now what will be work done then? Work done will be Fx, so I dot I, so Fx times x final minus x initial, and I can call that delta x. Fx delta x plus similarly Fy will get multiplied to delta y, Fy delta y plus Fz delta z. Okay, so this I can write as another beautiful notation for writing work done. Okay, so these all the cases I have discussed till now are based on work done by uniform force. Okay, work done by a constant force. So the force is neither changing in magnitude as well as direction, because when I talk about a vector to be constant, it should be constant in magnitude as well as direction. So, and what if force is not constant? What if force is not constant? So before going to the numerical problem solving session, so let me talk about work done by variable force. So till now we are talking about the simplest case. See, I started with the simplest case, constant force and force in the same direction as displacement. Then constant force, but there is a particular angle between force and displacement. Now I am removing those assumptions of constant force, and I am taking on a more general case, that is work done by variable force. So now the force is variable. Now if the force is variable, you can clearly see that if the force F is applied here, this will not remain F for the whole journey. So this will not remain F for the whole journey. So what to do now? So that means this F is constantly changing. So for every small displacement, work done is different, because work done depends on force, and when the force is changing, work done is changing. So that means I should not be defining the work done for the whole case at once. What I should do, I should take the calculus approach. What is the calculus approach? If you have a problem, big problem, break it into the smaller problems, and then go for that smaller portion, study that smaller portion, and then integrate to get the whole thing done. Okay, so similarly what I'll do, I will say that the force F is applied and this F remains constant over a very small displacement delta x. Okay, or this delta x should be very, very small. So I will not call this delta x, I will insteadly call this dx. I'll call this dx, very, very small displacement. Okay, delta is change in x, but d is very, very small change in x. Okay, so dx, f dx. So if I say that this mass got displacement from here to here, I'm not calculating the work done from here to here, I'm just calculating work done in this portion. Okay, so that will not be the whole work done, that will be the small work done. So I'll call that dw, the small work done for this small displacement dx, and over this displacement I assumed force to be constant. Okay, because the force is not constant, but if I take the interval to be very small, if I take the displacement to be very small, then it is very, very safe to assume that this force remains constant over this displacement. So f dx, f dot dx. So dw is equal to f dot dx. So this is the small work done over this small displacement dx. Now if I want to get the whole work done, what should be my approach? I should integrate it. So to get the whole work done, dw, I'll integrate it and I'll have integral f dot dx, and this thing will give me work net, and that will be equal to integration of f dot dx. Okay, and if you see that this is the most general case, because here I have no assumption. I did not take the assumption that force is constant. That's why I'm taking the integration sign. Okay, and I'm taking the calculus approach. I did not take the assumption that dx and f are in the same direction. That's why I kept the dot product between them. Okay, because that dot product will incorporate the cos theta term here. Okay, and that cos theta term will have theta, and that theta will be responsible for the direction, okay, for the angle between force and displacement. Okay, so f dot dx, and you can see that this is the most general case, and I will get the special case that force is constant from here. So if f is constant, I'll say that if f is equal to constant, that what I can do. So when the thing is constant, there is no need of keeping it inside the integral. So what I can do, I can say that w net is equal to f dot integral dx. Okay, and what will be integral dx? That will be the whole x, that will be the whole displacement. Okay, so f dot s. Okay, f dot s. So here I have assumed that, actually I have taken this, in this case I have assumed that the things are going in the x direction only. Okay, so f dot s. So whatever will be the total x traversed, that will be the total displacement in this case. So this is the thing that we talked about earlier. Okay, so this is the general case, and from the general case you can get the special case. So you need to remember this thing. This is very, very important. Okay, now let's move on to some problems. Okay, so to start with, I would like to give you a very, very simple problem. What is the problem? So suppose that force F is equal to 2I cap plus 3J cap acts on a body, and displaces it from 1, 2, 3 to 2, 3, 5. So what I'm actually giving you, I'm giving you the initial coordinates and the final coordinate. Why I'm giving you? So that when you subtract these, you get the displacement. So the question is, find work done by force. Find work done by force. So clearly you can see that what is the displacement vector? Displacement vector will be x final. See, this is x initial, y initial, z initial, x final, y final, z final. Okay, so x final minus x initial, that is 2 minus 1, that is 1, and that is I cap, plus y final minus y initial, 3 minus 2, again 1, j cap, z final minus z initial, 5 minus 3, 2k cap. So this is my S, displacement vector. And what is the force? Force is clearly given to be 2I cap plus 3j cap. And when I do the dot product between these two, I would get work done as, in the dot product, I will take I cap with I cap, that is 1, 1 into 2 is 2, plus j with j. So 3 into 1 is 3. And then 2, k cap. And here k cap is absent, so I can assume that it's actually 0 k cap. Okay, 2 into 0 is 0. So 3 plus 2 is 5. So the work done is 5 joules. Okay, so this is the case when the force is given in the Cartesian form. Okay, vector form and the Cartesian form of the vector. Okay, so where I have been given the coordinates and their directions. Okay, so this is the case. In some cases, what I can be given is that see, that can be very simple thing. There could be a force given, like for example 10 Newton. Okay, the 10 Newton force is being applied and the body is getting displaced by 5 meters, and the angle between them is 60 degrees. Okay, so this can be the case. If this is the case, then you know that this is the magnitude angle way. Okay, this is the magnitude angle form. So what you are given, in the previous case you are given the Cartesian form of the vectors like I cap, j cap, k cap. Okay, and now you are being given the magnitude and the angle between the vectors. So magnitude is 10, magnitude is 5, and the angle is 60. So what is work done? Mod f, that is 10, mod s, that is 5, and cos of 60 degrees, and cos 60, that you know is 1 by 2, and that will make this 5, so that will be 25 joules. Okay, so these can be the simpler cases. Now let me tell you one more thing. Okay, and before going to a more interesting problem, I would like to tell you one important thing. And what is that important thing is that, see, since initially I told you that work and energy are actually the two sides of the same coin. Okay, so remember one thing, what I'm going to tell you. I'm going to tell you one thing. See, until it's done, it is work. And when it's done, it becomes energy. So what is work actually? Work is actually energy in transit. Okay, so work is actually energy in transit. See, for example, if there is a mass m and I apply a force F on it, initial velocity was 0. Okay, for example, after some time the velocity becomes 3 meter per second. So when I was applying the force on this, and the body was actually under the influence of the force, and under the influence of the force it took some time for the body to change its velocity from 0 to 3 meter per second. So what actually happened? What actually happened? Until it was done, I was doing work, and when I am done, I would have the kinetic energy in this as half of mv square. Okay, so what I did actually, I did work on the body, and I made that work convert to the kinetic energy of the system. Are you getting my point? So I made that work convert to this. So actually what is happening, whatever work I am doing on the system, it is somehow being manipulated as the energy of the system. Okay, or either I can even say that the reverse of this. For example, a body was moving like with a velocity of 3 meter per second, and then after some time I apply an opposing force F on it, and after some time t, it stops. So what I am doing? I am doing the negative work now. See, here I was doing positive work and the kinetic energy was increasing. And here I am doing the negative work because body is moving forward and the force is backward. So what I am doing? I am doing the negative work. And what is negative work doing? Negative work is making its kinetic energy decrease, because here the kinetic energy will be 0. Here the kinetic energy was from 0 to half of mv square, and here it is from half mv square to 0. So what actually is happening, whatever work I am doing is being manipulated or is being manifested as the energy of the system. So with that said, I would not just jump to work energy theorem. Okay, I would not just jump to work energy theorem, but I would like to discuss a very beautiful problem, and for this session this will be the last problem, and through that problem I would like to make connection between this topic and the work energy theorem. So I would like to make connection between work and energy through that problem, and that will be the last problem for today. Okay, so let's discuss that problem. Okay, so see, what is the problem? The problem is there is an elevator. Okay, so there is a lift, and inside this lift there is an inclined plane. There's an inclined plane which is making an angle theta with the base of the lift. That's making an angle theta with the base of the lift. And on this incline, there is mass m. There is mass m. Now try to understand one thing. What is happening that this lift is moving up with the velocity v, and this velocity v is constant. So the lift, the whole system is moving up with constant velocity v. So the question is, tell me how many forces are there acting? How many forces are there acting? So the first thing is, obviously, if it's mass and it's in the gravitational field, there will be mg force downwards. And if there is a surface and they are in contact, there will be the normal force. And let's suppose there is a frictional force here. Okay, so there is a frictional force here. Okay, so because this is standing on this, so there is frictional force. So F. So there are three forces: frictional force, gravitational force, and normal force. So the question is, find part A. Part A is find work done by gravity. Okay. Part 2 is work done by normal. And part 3 is work done, you have to find work done by friction. Okay. And the part 4 is work done by all forces. That is the net work done. Okay. See, actually this the part 4 of the problem is actually the connection between the work and energy. That's the work energy theorem. See, let me tell you one thing. The three parts I will solve in front of you. But can you use your intuition and tell me what should be the answer for the fourth part? It seems that the fourth part should be the most tough, but the fourth part is the easiest one. See, you have to be very, very careful here. Velocity is constant. Velocity is constant. So that means kinetic energy is not changing. If kinetic energy is not changing, therefore work is not being done. Because I told you, if the kinetic energy was increasing, positive work was done. Kinetic energy was decreasing, negative work was done. So what does that mean? That means if the kinetic energy is not changing, then there should be no work done. So net work done should be 0. But it is just the intuition I am giving you. But let's try to calculate it actually. So first of all, let me talk about work done by gravity. See, you can clearly see that if this is the mass m and mg is the force on it, and suppose in time t it moves up with velocity v. So what will be the displacement? S will be vt, because velocity is displacement upon time. So what is displacement? Vt. So you can clearly see that mg force is downward and displacement is upward. So clearly the work done is negative. Why? Because the angle will be 180 degrees. Okay. So angle is 180 degrees. So what is the work done by gravity? Work done by gravity will be equal to force of gravity, displacement, and cos of 180 degrees. So force of gravity is mg, displacement is vt, and cos 180 is minus 1. So work done by gravity is minus mg vt. And clearly you can see that, you can directly say that work done by gravity should be negative. Why? Why you can say that? Because you can clearly see that the gravity wants the body to move down, but the body is moving up. I told you that when the body is moving against the will of the force, then the work done by that force is negative. So work done by gravity is this. Okay. So now let's talk about work done by normal force. Work done by normal. Now see here, the normal reaction is like this. Okay, normal reaction is like this. If this angle is theta, then this angle is also theta. This angle is 90 minus theta, so this is again theta. Why? Because this is 90. This is theta, alternate interior. And then this is 90 minus theta, because this is perpendicular to the surface, normal reaction. So this is 90 minus theta, then this is again theta. So normal is like that and displacement is like that. So what we have, the situation is something like this. Normal force is like this. And this is the displacement S. And what is the angle between them? Theta. So what will be the work done by normal? It will be NS cos theta. NS cos theta. But what is N? What is N? See, this is N, this is mg. mg has a component here, mg cos theta. So actually, mg cos theta is trying to get this block inside this wedge. But N sin theta is trying to get this block above this wedge, like this, in this direction. Okay, it's trying to elevate this. But neither it is elevating nor it is getting down. So that means these two forces should be balancing. So N should be equal to mg cos theta. So I can write work done by normal is equal to mg cos theta, and displacement you already know is vt, and then again cos theta, that will make it cos square theta. So what is work done by normal? Work done by normal is mgvt cos square theta. mgvt cos square theta. Okay. Now let's talk about work done by frictional force. Work done by frictional force. You can clearly see that this is the frictional force and this is the direction of displacement, because the lift is moving up. So what will be this angle? I clearly told you this was normal and this angle was theta, and this is friction. So what is this angle? 90 minus theta, because normal and friction are clearly perpendicular to each other. So if with the normal displacement is making theta, then with friction it should make the complementary angle, 90 minus theta. So what should be the work done by friction? It should be frictional force into displacement into cos of 90 minus theta. Why? Because you have to take the cos of angle between them. So that's 90 minus theta, and cos 90 minus theta is sin theta. So work done by frictional force is equal to Fs sin theta. Fs sin theta. But what is F? You can clearly see that mg has one component like this, that is mg sin theta. And mg sin theta is balancing this. Okay, because maybe I have forgot to mention this, that this block is not moving relative to this wedge. Okay, so you have to assume that this block is not moving relative to this edge. Okay, so block not moving relative to wedge. Okay, so that's the condition. So if mg sine theta is trying to get this down, f is trying to move it up. Okay, actually f is not trying to move it up, f is actually trying to balance that mg sine theta. But so when it is not neither moving up nor going down, so they are balanced. So what is f? F is mg sine theta. So what I can say that work done by frictional force is mg sine theta. And what is S? S is Vt, and then again sine theta, so it is mg sine square theta Vt. So this is the answer for part A. This is answer for part B. And what is this? This is the answer for part C. And what is the answer for part D? Work done by all forces. So that will be this plus this plus this. So work done by all. So work done by all the forces will be equal to what? See, work done by all the forces will be equal to minus mgvt plus, see, mgvt sine square theta, mgvt cos square theta. So I can take mgvt common, and inside the bracket I have sine square theta plus cos square theta, that is 1. So minus mgvt plus mgvt, that is 0. And that was the answer I gave you initially due to the intuition I applied on this. Okay. Now, so this is the problem where you could have answers. So if the question did not ask you about these three parts and ask you about this part directly, then you need not to calculate these three and then add them. Okay. You can directly go with this thing. Okay. So now let me just conclude this lecture by giving you a homework problem, and that homework problem will be the connection, and through that connection will enter the work energy theorem. Okay, so let's talk about this. So this is theta. Now the same problem as previous. Wait, make it better. Sir, problem to bus. So this is theta. Okay, so this is theta. Now again the same thing, mass m is here and there is no relative motion between mass and the wedge. Okay, so there is obviously frictional force and there is normal force and there is mg. Okay, but now instead of what, instead of constant velocity motion upward, I am giving you constant acceleration motion upward. Constant acceleration motion upward. So the question is again, find work done by gravity, work done by normal, work done by friction, and work done by all. Again the question is same. Now you can clearly see that work done by all the forces will be equal to what? Change in kinetic energy. Again, okay, I am giving you directly the answer for the fourth one. The answer for the fourth one will be work done by all will be equal to change in kinetic energy, that is half of mv square, half of mv square. And what is acceleration? Acceleration is v by t. Okay, acceleration is v by t. So we have to find work done by gravity, work done by normal, work done by friction, and work done by all in time t. In time t, because time t should be the parameter given in the question so that I can use it to find the answer, because the answer should always come in the parameters that are given in the question. So a is vt. So what is v then? V is at. After time t, the velocity will become at. So the answer for this will be half of m vt whole square. So what is your homework? Your homework is half of v is equal to at. Yes, sorry. Yes, so half of at whole square. So what is your homework? Your homework is to verify this answer, that work done by all the forces is this. So what you'll do, you'll calculate work done by gravity separately, work done by normal separately, work done by friction separately, and then add them and then tell me if this is consistent with this result. Okay, so thank you very much. We'll be discussing the other topics in the next lecture. Okay, stay blessed.